Hello, my name is Grace. I'll be showing the YouTube videos of how we did part A, B, and C. I'm gonna first start off with part A. First we did is we created this geometry here. We made sure it was in 2D over here on the right. Gonna show the geometry in Discovery. So in this Discovery, the geometry we created this, this is our inlet area over here and our outlet, and this is our test section that we did. And on the end point of these test sections, we created a construction line. This will be useful in kind of dictating where our, or different, like differing like the inlet versus like the diffuser area and the test section. So dimension wise, we did this one at about 1.6 meters, 1.6 meters, 1.2 meters, same on this side. This 1.2 meters, 1.22, 1.5, same on this one, and then our diffuser outlet is 0.889. And we went ahead and labeled everything. So I'm just going to show you. We don't really need this to show. Okay, so our inlet is on the left. This is our outlet here on the right. Our top is the 3 top surfaces right there, and our low are the bottom 3 surfaces right there. 1, 2, 3. So that is our geometry. So go ahead and close that out. We're going to go ahead and look into what we did for our mesh. Okay, so here's our geometry in our mesh. The first thing we did is we added this test section right here, which was our sizing. Our sizing for the test section, the top layer and the bottom layer. For this as our geometry, we changed this to number of divisions at 500 with no bias. Next, our nozzle area, we selected these top 2 edges right here, and with a bias factor of 3, our reverse bias is going to be just one of these edges right here, and we wanted to make sure we make this to number of divisions at 500. Our diffuser over on the right side, we selected these 2 edges for our geometry, and down here for our reverse bias, we also selected one of those. We want to make sure it's also number divisions, 500. Our bias type is the same as the nozzle, and at 3 for the factor. The inflation, we selected the geometry face. Boundary layer is, or boundary edges are going to be these 3 along the top, excluding like the inlet and outlet. Our first layer height is at 1 e to the negative 0.005. We want 60 maximum layers at a growth rate of 1.1. We also wanted to make sure we added the triangles method. On our geometry, we selected the entire body, and everything else there is good. And here you can see our game selections that we discussed in the geometry discovery. So we can go ahead and regenerate that mesh again. So this is what it should look like. We have a finer number of particles on the outer edge of our geometry, just so we can get more accurate results and see what's really going along those edges. So we can go ahead and exit out of this now, and then go into our setup for part A. I want to make sure it's at double precision, and my computer runs pretty good at 4 for the solver processes. So we get that all set up, wait for it to load. Okay, so now that is finished, we make sure all of these are the default settings. In our models in our viscous, we want to make sure K omega, all of this remains the same. So that's good. Our cell zones, for our fluid, that stays the same. Boundary conditions, as we just want to make sure everything changes. When we change our velocity magnitude, we calculated our velocity to be 5.6, because for of a test section velocity of 15 meters per second, we want to make sure it equals the correct contraction ratio. So by applying those into the correct formula, we get the velocity magnitude of 5.625, and all the rest of these numbers will stay the same. For our outlet, just want to make sure that these are all the same. Our internal, our low wall should be no slip stationary. Yep. Roughness constant 0.5. Our top wall should also be the same conditions, no slip. And close that. Okay, so our reference values, we should see our viscosity, we don't want to change, we just keep that at the constant, change that to the surface. There we go. Okay. So yeah, that should be from inlet, because we want this velocity in our inlet. Now let's go check out our residuals, which I'm going to change these to 1e to the negative 0.06. Okay, that looks good. For our fluid, that stays the same. Boundary conditions, as we just want to make sure everything changes. When we change our velocity magnitude, we calculated our velocity to be 5.6, because for a test section velocity of 15 meters per second, we want to make sure it equals the correct contraction ratio. So by applying those into the correct formula, we get the velocity magnitude of 5.625, and all the rest of these numbers will stay the same. For our outlet, just want to make sure that these are all the same. Our internal, our low wall should be no slip stationary. Yep. Roughness constant 0.5. Our top wall should also be the same conditions, no slip. And close that. Okay, so our reference values, we should see our viscosity, we don't want to change, we just keep that at the constant, change that to the surface. There we go. Okay. So yeah, that should be from inlet, because we want this velocity in our inlet. Now let's go check out our residuals, which I'm going to change these to 1e to the negative 0.06. Okay, that looks good. I want to add our surfaces on here. We want to add our center line, which is, we want our XO to be negative 1 point. So this should be center line. Now we want to make our line for our vertical distribution. I'm going to quickly go back into our geometry to find this. Okay, so our center line should be from their y should be 0.8128. Eight, 8128 to 3.9. Our x is going to be 3.91. And then our second y is going to be the same. Now we're going to do the same thing for our vertical line, which is going to be from 1.7, 1.726 to same number to 0.5. and put those numbers in here, 1.726. We're going to round that to 7. And then our y value is 1.1165. Okay. Now our second x value is the same. 6, 7. And then our y value is going to be 0.5090. Okay, now we have those two things. Now we can run to our initialization. And then we can run our calculation. And make sure this is at 1,000 iterations so we can capture the entire solution. Okay, so now that our calculation is complete, we can... Okay, so now we are going to get our pressure contours. So we're going to go into graphics. This is going to be pressure contour. Actually, we'll name this the static pressure contour. This, we're gonna have it on the center line. No, we're gonna have it on our surface. And then go ahead and display. So that is our static pressure. As you can see, it's pretty high up on the left side in the nozzle area, and it gets a little bit less static pressure in the test section area. Now we're going to create our velocity. Velocity magnitude off of the surface. And that looks good. This is our velocity magnitude. Then we're going to create our dynamic pressure of the surface. This is our dynamic pressure. then we are going to make our total pressure off of the same surface. And yeah, this one's going to be pretty high pressure all throughout the system. Up here is a little hint of green, just on the outer parts up here. Okay, so now we're gonna add in the streamline. Velocity stream function. Actually, I'm gonna do this in the results tab. So we're gonna save that. Okay, now we're going to plot the variation along the center line. So we went over our different contours that we have. So now we're going to go into our vertical distribution of our velocity. We want to make sure we use our velocity magnitude here and make sure it's at our vertical distribution. And that will give us this graph right here. Now for our vertical direction distribution of our dynamic pressure, we will have our x-axis as our dynamic pressure and make sure our plot direction is changed to this right here, and this will give us this graph as our dynamic pressure. Now let's go over our total pressure for our vertical distribution. So here we'll have our x-axis as our total pressure, vertical distribution, nose values, y-axis, and that is our total pressure right there. Okay, and then our static pressure, we have as our x-axis is our static pressure, vertical distribution, and this is what our static should look like. Alright, so now we can go on to our center line. So our center line, our y-axis is going to have our flow of the velocity magnitude. We change our plot direction and on the center line here. And this is what our graph should look like. And our dynamic pressure, we're going to have as our y-axis, dynamic pressure, center line, plot direction is 1. And close that, dynamic pressure. Our total pressure, our y-axis is our total pressure, center line, and these are what we want for our options. So this is what our total pressure should look like. And last but not least, we'll do our static pressure on the center line. So y-axis, static pressure, plot direction, and everything else. And that is what it should look like for our static pressure. Okay, so now I went over all of our plots. I want to quickly go over our stream function. So in our contours, we want to add a contour, name it velocity stream function. This contour will be velocity stream function, and we want this on our surface. And we want to make sure it's smooth coloring, and we go ahead and display that here. So this is what our contour stream function should look like, and you can see it's pretty red up at the top, whereas it's pretty a lot more blue on the bottom, and that kind of dictates how how it varies between the diffuser and the test section and the inlet area, the nozzle area. And that is it for part A.